Let's get started. So thanks everyone for waking up. So we've got a full day of people visiting for NERPs coming to give talks. First one's Amrit coming from Florida. Right here, housing prices are doing great right now. We can send some of that north. I used to be of Maryland, right? Yeah, and work on all sorts of things like RL and alignment. So let's welcome Amrit and get this started.
Thank you, Mark, for the nice introduction. So I have huge respect for his research, and I have actually utilized that in my PhD for all the proofs of strongly convex PL objectives. So recently I've started working on reinforcement learning, and I'm going to present inference time alignment of large language models for this talk. So as a quick introduction, I'm an assistant professor in computer science at University of Central Florida. Before that, I was a research assistant professor at University of Maryland, and before that, I was a research associate with the US Army Research Lab. So let us start with this question, which everybody is trying to wonder about, like, is it really going to happen that like we are going to use AI for everything? For instance, can AI, or just imagine a world where AI can really do diagnosis for us with 99% or 100% accuracy. It can drive us through the busiest streets, and it can really be a tutor also for our children. Then the question is, among all these promises, are we there yet? And the quick answer is, of course, not. And then I will try to go through the motivation for my research, try to answer this question, what are the things which we need to do, and then go into deep detail of one of the aspects on which we have to work. So if we look at the recent breakthroughs in artificial intelligence, AlphaGo, which came in 2016, then AlphaFold in 2018, AlphaTensor in 2022, then last but not the least, this is not a comprehensive list, but the main things in the last 8 to 10 years. Then came ChatGPT, which actually changed a lot of things, especially the academia, and you can clearly see a big contrast even between the publications in URIPS or ICML in 2021 or 2022, and now if you see 2023, 2024, major things are covered by large language models. It has a huge impact on even on the research communities. So what are the problems associated with this, and then how what we can solve from an academic community? I'll discuss them in brief detail. So I think I don't need to define AI for this audience, but still just to cover the basics, I'll take a step back and then try to answer in a very simplified manner. The definition of AI is nothing but trying to learn the data distribution, and if the data is of the image and label form, it means we are trying to learn a classifier. The data is a prompt and image, and we have our diffusion models to learn this distribution. The data is of the form text and then the next word, and that is what our language models are trying to do, learn the distribution of. And then the data is of text and video. We have our stable diffusion models for video, and so write an example of that. So for the purpose of this talk, there are different, all these things are also considered artificial intelligence. Just for this talk, whenever I'm referring to AI, I mean large language models. I'll stick to that as an AI concept. So how does it work? So we have a large language model. We give it a prompt, for example, prompt or query or say input, and we ask what is the capital of France. And what it does is it generates the first token or word, say Paris, and then concatenate it with the input, and then generates the next token, Paris is, and then combine them again with the input and keep on doing that to generate the full response till it samples the end of sentence token, and then it will stop. So that is the input, and the output is generated one token at a time. This is called token by token generation, and then so there is an input set of tokens, there is an output set of tokens, and then you can utilize this characteristics of the language model in robotics area, healthcare, finance, and education, where it actually depends on like which area or what kind of input is coming from, and then it needs to operate on that and generates a set of output. For example, in robotics, the input could be a set of instructions, and the output could be set of sequence of actions which my robot needs to take. So how to obtain such a model? So the standard practice, we call it pre-training, but before it was just the training, self-supervised training of language models. So what we used to do is large corpus of text data on which we try to train these models with the loss as next word prediction, and we want to minimize that. And that is actually have been utilized in the various development of language model even till 2021. But these models were still not behaving like as we see them today. Like it has become very difficult to differentiate between human written text and the language model written text. But before 2021, it was not the case. You could have easily differentiated between if something is written by machine or not. So what comes after this, which actually made this huge breakthrough? There are additional stages which comes to this pre-training. The first is supervised fine-tuning. We collect a high-quality data set and try to fine-tune our pre-trained model in a supervised manner, and then use that model to collect human feedback. Like we show or we collect the responses from supervised fine-tuned model, and then show human and collect their preference feedback. Like the easiest thing is we generate 2 responses for a given prompt, and then ask the human which one you like, and then using that we do reinforcement learning based fine-tuning. And this whole 3-stage process is called the alignment. And this is what is being added to this pre-trained model after 2021, which actually led to ChatGPT and then all the models which we see today. So they are a combination of these 2 stages. One is pre-training and then the alignment. Or we also call it like pre-training and post-training. Alignment is also called post-training. But even with this, what are the issues which still remain and then we need to address? So there are safety issues. There is a famous paper from the group where they say that, okay, we have trained our model, be it ChatGPT, Anthropic, Google, or Llama 2. And if you ask the model, okay, generate a step-by-step community, generally it does not respond because there are safety filters. But if you add an adversarial prompt to that input, it will give you a very detailed answer to this question. So this is in accordance with the adversarial attacks on classifiers in the image domains, but these are like new for this language model kind of space, but they are like safety issues. Think of it like maybe generating this response is not that serious, but there could be other cases or applications where somebody can really prompt an LLM to do really bad things. That is where this comes into picture. So the overall concern here is you can make LLM do whatever you want it to do. That kind of control you can have with this adversarial prompt, which is a bad thing. Then comes the reliability issues. The reliability issue is in this paper. For example, a question is you ask who the first person to walk on the moon, it gives a very nicely written, grammatically correct answer, which is wrong. Right? There's a factual incorrectness, and we know the correct answer, so we can check it. But think of it, if somebody think of applying it in the education field or tutoring the children, because they don't know the correct answer, they might learn wrong things from here. There are issues with this. And the second example is, even if it is not about the factuality, if you just ask it, oh, can you summarize this text for me? And then in summarization, what it did, it added 2006 with October. And maybe that's happening because in the data when it was like getting trained, October 2006 was actually the main thing in the data. These are like, you cannot rely on LLM. So these are issues in the model. And then last but not the least, there are robustness issues. Robustness issue means if you change a little bit in the prompt, even if that change was not intentional, it may lead to a huge change in the output. For example, see this prompt, and there is this question sample where the answer is just yes or no. There's a question, see of A, and then a composite number, say yes or no. So when you prompt it, as a mathematics instructor, calculate the answer to the following problem related to. And in that, there was a very natural spelling mistake, like instead of U, you wrote E, and then W, you wrote X, right? They're very close on the keyboard. So when you do that, it just given wrong answer rather than giving the right answer, while the prompt was very nice. In a similar way, even just to get the sentiment of the sentence, just because there is not even a spelling mistake in the second part, but if you see the sentence is not completely grammatically correct. He's asking analyze this assertion, and defining whether it is a positive or negative sentiment. And it is not very cleanly written, just that led to a wrong answer in the output. So it is not very robust with respect to the changes in the prompt also. So how can we deploy these systems to our real world applications in robotics, education, finance, or healthcare if those issues persist in this model? So that is what is the motivation for my research. I try to work on safety, robustness, and reliability aspects of all these systems.
Quick clarification on robustness. You also look at robustness as in robustness to injection noise.
Yeah, so
Stuff like that.
of course that is also robustness issue. This is just a simple example, but yeah, means that robustness to noise. I would even consider it in the first case, like safety issues. So if you add a noise, the output would change. So they are not very cleanly separated. Like, but yeah, means if there is a change in the input, then lead to change in the output. It comes in the robustness issue. And that change could be due to spelling mistakes, due to noise, or due to even like inserted noise or injected noise. So they all comes under the robustness issue. Yeah, so that is where my lab focuses on, and these are the different aspects on which we are trying to focus on: the alignment, security and privacy, explainability, mechanism design, uncertainty quantification, and energy efficient AI. And they all are connected with the fundamentals of utilizing optimization methods to develop new algorithms such that we can achieve all these goals. So in this talk, I'm going to go deep into the alignment aspect of things and tell what we actually did. So this is a paper which I'm going to present in detail. This is a work in joint collaboration with wonderful collaborators from Princeton and University of Maryland. So I'll start with motivation of AI alignment, what is tuning-free alignment, and then fundamental challenges and our key idea, and then conclude and provide some future directions. So now let's talk about what is AI alignment. As we have seen a lot of issues in the AI, and what it says, if you do the Google on IBM research website says, alignment is the process of encoding human values and goals into AI models such as large language models. So essentially what we want is AI model should behave as we human want them to behave. That's the alignment problem. And in terms of its importance, if we have an LLM, there are different values and there are safety concerns as we just discussed. And quick example is, okay, if this again goes with the safety issues. So how to make a bomb? We should ideally say, sorry, I can't assist you with that, and should not generate the answer, okay, to make a bomb, here are the details. So this is an alignment problem. So we want it to generate the first answer, not the second one. And there are ethical issues. If somebody asks my LLM to write a spam email, it should not do that. And there are trust issues, as like if you ask it, like who is Tom Hanks' mother, it will give you an answer. But if you ask directly his mother's name, it say, well, I don't know. Because, and you can see the reason, because I think on Wikipedia, there are articles on Tom Hanks, but not his mother. So in those articles, maybe it is written that Tom Hanks' mother, but directly it is not able to answer. These are weird things. Right? And then last but not the least, there are society or social norms among the humans which our language model should comply with. For instance, if we ask it to provide me an example of good family dynamics, there could be two possible responses: where traditional roles where women manage households and men provide, and then shared responsibilities and open communication among all the members. So we really want to align it with our social values. We want our LLM to generate response to, not response to, and could have generated both. And yeah, so these are the issues we want to solve. And we say we can solve it with alignment. We want our LLM to align with all of these values. And what are the standard approaches in the literature? And there are fine-tuning based approaches. It's called reinforcement learning from human feedback, which I just mentioned. They generate the responses, collect the feedback, and then do reinforcement learning with fine-tuning. And PPO is the main algorithm which is used to do that. And there is recently a direct preference optimization algorithm, which is essentially doing alignment, but it is an advanced version of that. But all of these methods are fine-tuning based. By fine-tuning, it means we have the language model which has like billions of parameters. We actually change those parameters to align it with whatever we want. But the challenges of this is there are billions of parameters we would need to update, and it would be computationally really heavy because we need to calculate the gradients and then do the updates. But why is this even a concern? Like if was OpenAI did this only, they changed the parameters. So, and what we are trying to motivate is from a general perspective, this is not the solution to alignment. Why? Because there is not just one human or like one values attached to it. Like you just align with those. There is an inherent diversity within the humans, and we might want our model to align with different values. But if we go by the fine tuning route, what it would ask is, it would ask us to align our LLM to all of these different values. And think of doing fine tuning for all different these human subgroups, which would even result in a huge cost, and then it won't be practical. And diversity is not only the issue. The changes in the preferences is also another concern. Like you think of it like we spend millions of dollars to align with some human data we get, and after 4 years, the human preferences changes. So we might need to spend the whole money again and then keep on doing. And then we have a recent example, I think, within the world, before COVID and after COVID world is already very different in terms of what human prefers, especially in India. A good example in terms of movies, people have stopped going to theaters and started watching Netflix more at home. So clearly there's a shift in the preferences. So movie changing preferences is a concern, and fine tuning cannot be the solution to that. And there are privacy concerns for fine tuning. You really need to collect the human feedback, human preferences with you, and then you do the fine tuning. So as the awareness in this data sharing or data collection things coming among the humans, they are becoming less and less comfortable in sharing their preferences with the companies or with the data collecting companies. And then last but not the least, fine tuning requires you access to the model weights. That's what otherwise we cannot do. For instance, there's no way we can do fine tuning with ChatGPT or OpenAI's model because we don't have access. We can only do fine tuning on the models for which we have access to the weights. And I cannot train my own language model; it's too costly. So how will I do so? Thanks to I think Llama models, they are open source, and then we can still, if we want to do, we can do fine tuning. But there are lots of challenges. So then what we do? So these are the things which we knew that okay, fine tuning can help me with alignment. But if I am saying okay, we should not do fine tuning, what else we do? And that is where the answer comes in. We say that there is another method which we can utilize to do the alignment. It's called alignment via decoding. What is the decoding process? I think I have already discussed this. This token by token generation, when you give a response, this actually is called the decoding, this token by token generation. And you can see you give it the input, you are generating it one by one. And the whole idea is rather than changing the parameters of LLM, let's change this generation process. Let's steer it to whatever we want, and we will use that process to do the alignment. Now I'll go into the mathematical formulation of that. And big question is, can we utilize this decoding for alignment? Quick answer is yes. But to exactly show how we can utilize this, let us try to formulate the problem. We need to define a Markov decision process where state space is nothing but concatenated sequence of tokens, and you can think of it like space of all possible sentences in the world. And then the action is the next token, which is nothing but the action space is the whole vocabulary, and the action is I need to pick the next word which I need to select, right? So my action is the next token. And the transition here is deterministic. Why? Because as I'm generating what is the capital of France, I generate Paris as the first word, and then my next state is my prompt concatenated with Paris. So there is no ambiguity in that. So it's like a deterministic. There is no randomness here. And then last but not the least, the reward function, which is actually responsible for alignment. You might have wondering like how can I actually tell my LLM what to do? Because if a human wants to change the behavior of LLM, there should be some way to signal that to LLM, and this reward function works as a signal. And you can think, I'll check the response of my LLM. If the reward is high, it means it is doing what it is supposed to do. If the reward is low, it is not doing that. I should change my LLM in a manner that the reward is high. And I will call that alignment. That's what alignment is. This is the notation. We denote the language model as a pi, which is also used for policy in reinforcement learning. And then how it works is a little bit of mathematical notation. So at each token t, we are given a state where x is the prompt, y strictly less than d is the tokens we have generated so far. which essentially lies in the state space. And then this y is just the token so far. And then for a given t, we generate yt, which is a sample from pi given st. So that's how it works. And pi is called a token level decoding policy because it is telling me each token for a given state. And then we repeat this process for t equal to 1, t equal to 2, t equal to 3, and till end of sentence token. And this is, you can see, is actually the decoding process which we are going to utilize to do the alignment. Yes. So this is my TS level probability of yt given my state, and then we take the product from t equal to 1 to capital T of generating all the sequence of tokens, and then we denote it as rho pi, which is actually used in the literature of fine tuning. So what is the difference between left hand side and right hand side? It will become clear by I'm defining this. The right hand side is actually the token level probabilities, and then take the product. Left hand side is the trajectory level probabilities, you can say. So it is saying for a given prompt x, what is the probability of y, and we are calculating it just by taking the product of generating all the tokens. So as an example, so x is, you can connect it with the earlier example. X is actually what is the capital of France, and then this Paris is the capital of France. Y0, Y1 is actually the tokens, and then this whole thing is actually my. And then there is a reward model which we assume we have access to. There is a different, this is a different question, or you can ask like how to obtain such a reward model, and that is where you need to collect human preference and learn that. So you might have access to a ground truth reward, but for the sake of discussion, we assume we are given a reward model, and that reward model will actually guide me how should I do the alignment. So what it is trying to do, it will take x, it will take y. If this is correct, this will give me a high score. And just imagine if it would have answered it like what is the capital of France, and Washington DC is the capital of France, and I give that pair to this reward model, it should give me 0 or very low. And but if it put Paris there, then it gives a very high. So that is why that is it's an important reward model. It give me a score. But this is a trajectory level reward. So we have our token level policy, trajectory level, and then the reward model. And this is the fine-tuning objective of alignment. So this equation is what is AI alignment, to be honest. And then what they are trying to do here is, if you see, there is a reward model for a given x and y, and you can forget about the expectation over x, that is just across the prompts. But the main thing is this expectation over y from this trajectory level model, rho. What it is trying to say is, for a given x, I will sample my y and then calculate my reward and take the average. That's the first part of the objective, and there is a maximization. So what it is trying to do is it's trying to maximize the reward. We're trying to learn a rho or the model in a manner that will maximize the reward. But what is the second part? Second part is very important, and that's what it actually makes the alignment problem. The second model part is trying to do is, I want to maximize my reward, but I want to stay close to my SFT model, which was the pre-trained model or the supervised fine-tuning stage, so that I do not end up doing reward hacking, just maximizing that reward and then keep losing like whatever I have learned so far, because pre-training at SFT, a huge effort which has gone into actually learn that model. So that is actually why it is called fine-tuning. So I have my rho SFT, which is actually the supervised fine-tuning model, and then beta will actually control that. If you make beta 0, it will really go to maximize the reward. And then if you make beta very high, it will just focus on staying close to your SFT and then not focusing on maximizing the reward. The beta becomes a hyperparameter which we need to tune. But this problem, you can even think of it like there are two objectives or KL penalty formulation, but essentially the core crux is I want to stay to my SFT model while maximizing the reward. And if I can adjust the model a little bit, that's what I would say is my alignment. But here, if you see in this alignment problem, we need the optimization variable in this whole alignment problem. Yes.
Is that KL supposed to be inside the expectation for Y?
So here the optimization variable is rho, which means I need to change my language model. And then when people actually do fine tuning, because because we are parameterizing my language model with some theta, so this whole problem becomes an optimization over theta, which actually means I need to change the parameters. So that's why it's called fine tuning, becomes complicated. Now the thing is, if I want to do this decoding or a similar alignment problem at the decoding level, how do I go from this problem to that decoding level alignment problem? And there's another thing is this problem which is formulated in literature is also at the trajectory level, but decoding is happening at the token level. So that is where this interesting paper, wonderful paper which are published in I7 this year, which comes into picture, control decoding for language model, where they have formulated this mathematical problem for the decoding space alignment. And this problem is at the token level. This is not at the trajectory level. What it says is, if you see, the second part remains the same. It is a KL, but we need to note that it is at the token level policy pi, not rho. And then what it says is, you are at a given state as t. I just need to adjust my probabilities in a manner that when I take expectation over the action selection, just that token z, not the trajectory, my first part should be maximized. And what is this Q star? And that is very interesting. This is no longer the reward, if you see, because reward would come in the end, like when my trajectory is finished, right? But when I'm doing at the token level, at each token, I cannot just look at the reward and max. I need to look at the long-term reward, and that is where it is replaced, or it, like Q star comes into picture rather than actually the reward, because for each token, I need to know the value, like which one I should pick, rather than knowing the reward. So that comes from reinforcement learning literature. The first thing is my optimal policy evaluation. The second thing is closeness to my SFT model. And this Q star function is nothing but maximization of Q pi over pi, and then Q pi is nothing but this is the expectation. For a given AT, you fix state and action, and then you collect or complete the response, and then you collect your reward in the end, and then take expectation. And you can see that this is nothing but a long-term reward return for that action. And if I have access to the optimal Q function, I just need to select the action according to that value and complete the sentence, and then it would align. And this R is responsible for alignment. So if I change this to R to R1, R to R3, I can actually align to different rewards by keeping the same model, base model same, without even changing the parameter. That is the key part. So this is which is exists in the literature, and this is
What's the difference between rho and pi?
yeah. So pi is the probability of the next token.
Yeah.
And then when I generate, let's just say t length tokens like 1, 2, 3, and then multiply the probability. So that is what I call rho. So rho is a trajectory level probability, and pi is a token level probability. That's the difference. So once we have this, so this is a very nice, strongly concave objective, which has a closed form expression. Pi star is the decoding policy, and this pi SFT is my base model. And here you can see that it is a very standard way of adjusting the probabilities of my this token, and it will become proportional to my Q star, which is coming from reward. So whichever the token has high value, that will get selected in pi star decoding. And this remains same. I'm just changing the probabilities, and that is why this is tuning free. I'm not changing the parameters of the model, just adjusting the logics with which I'm going to pick my token. But this is the bottleneck here. So even though for the ease of exposition and writing the solution, we assume this Q star, but this Q star is actually assuming an access to pi star. So it could be like defeating the purpose, right? So I'm kind of assuming. So how do we deal with this? So this Q star is the bottleneck. So let's go deep and see what is the definition of this Q star. This Q star is nothing but long-term reward return under my optimal rho star. That's what it is. But this is not available. Rho star is not available. If it was available, then there is no problem to solve. So that is the chicken egg problem here. So what is done in the existing literature is, so that is the SFT model from where I start with pre-trained model. And I wrote just the equation there. You can connect like, okay, that part is the pi SFT. This pi star decoding is the one I want to achieve. And knowing Q star is the bottleneck. If I know the Q star, I can go from there to here in one go, no problem. But because we don't know that rho star, what existing literature proposes to use is replace that rho star with rho pi. But that's what I have. And I will get like not the correct estimate, but there will be some estimate of Q function. And when I use it, it improves the performance, but it does not go directly for the target because of this error in the estimation of the function. And this is what we fixed. This is the gap in the performance. So how to mitigate this gap? So we have this interesting, we feel it is an interesting observation. So what we think is why to use SFT model? Because we agree that we did not want to fine tune the model, like that was the goal. But there are already available fine-tuned model on Hugging Face. We are not doing that anymore. People have already spent energy and money on fine-tuning those models. So why don't we use those already fine-tuned models to actually estimate this Q star rather than using this SFT? But there comes the challenge that those models are not aligned with my target reward. They are aligned with some other reward. So that is what we adjust. We took those models, adjust the correction or the difference between the reward models and use that to do the fine tuning, and it works. That's what we do. And we call it transfer decoding. The key idea is there exists another baseline model which is aligned with some other reward, definitely not the target reward. And then we say that we will use that model to estimate Q star rather than using the SFT model, and then do the decoding. And then it is able to improve the performance. So the performance gain is essentially very precisely coming from a better estimate of Q. That's it. We are able to estimate.
So is that baseline model like aligned with different tasks?
Different reward, yes.
So a different reward, you mean like the same task but like different, I don't know, like for
Yeah, it could be like same task or different task. It actually, okay, that's a good point. So what it ended up happening is how different they are. Like they could be very different tasks. So if the rewards models are very, very different, theoretically you can still achieve this transfer. But empirically we see that if they are very, very different, it is hard to achieve the transfer. So there need to be some correlation. But the moment you make things proportional to the difference between, if we are able to calculate the difference between the reward models for a given token, then it works. We have that derivation. So why it is coming from? So this is the simple trick we use. So that is the, we call it TQ star, transfer Q star. And that is actually, the ideal thing would be if we had a row R which is aligned with the target, then the problem is easy. But we don't have, we have a baseline. So we multiply and divide by that baseline model. So the whole issue ended up is, how do we calculate this ratio? If we know this ratio, we will be able to estimate the Q as you're saying. How do we calculate this ratio? That is where we use the DPO trick or the closed form expression. And that is a closed form expression of a trajectory level fine-tuned model. It says that the baseline is actually equal to rho SFT times the exponential of 1 by beta R. And if you try to just do readjustments in the algebra and take the log, you can actually write reward in terms of policy in this expression. And we write it for rho BL, RBL, we write it for R. And then when you do simple algebra, subtract them, you can see that actually the weight ratio of rho R to rho BL is nothing but proportional to the reward difference between R and RBL. And if you exactly know the rewards those models are aligned to, you can actually calculate this weight using this expression and then put it in the TQ star expression, calculate the exact value of the Q function, and then do the decoding. So this strong concavity of the objective and this like a DPO trick which shows exploit the one-to-one correspondence between reward and policy model is actually helping us in this derivation. So then comes our proposed algorithm. We have the initialization, and then this is the baseline model probabilities, which the base model is trying to tell us to generate, but because we change the logics during the generation to do the alignment, that is where this proposed algorithm comes in. So we have two proposed algorithms. One is direct transfer, other is indirect transfer. In direct transfer, we assume we have access to the baseline model, which is already aligned with the target at the trajectory level, not at the local level. So this is like easy case, but to just go into the mathematical depth and understand, we do the direct case. But we have also extended the idea to an indirect case where we need to actually calculate the weights, as I just discussed, and then do the decoding. And once we have this TQ star, we use that TQ star to get the new logics and then sample our next token according to this new logics and then repeat this process. And this will do the alignment. So So in terms of theoretical results, we have shown upper bound for our suboptimality gap, which consists of two terms. The first term is actually the K divergence is a constant. The moment you know R, you know your rho star and rho SFT, that's a constant, but you can really make the first term become small by making your beta becoming close to zero, but that would end up paying price in terms of reward hacking. So there's a unique happening there. And then the second term, where this alpha is actually the decoding alignment parameter, and this h of alpha x is actually a positive term. So actually you can control how much this gap will be by just changing alpha and beta. And then we not only, because there were two objectives, we also show how close our model is to the SFT model, which is again ended up depending on the inverse of our beta and alpha. So in experimental evaluation, in this process, we take Mr. 11B for our SFT, and Zyper 7B for our baseline model, and this Mr. 7B for reward model, where reward model is trying to generate relevant, helpful, and ethical responses. So we did not do any fine tuning. These are all available off the shelf language models, and we use that to do the decoding. And then in our evaluation, you can show that in terms of reward, when we compare it state of the art, it is able to perform better. And it is important to actually also show the KI divergence objective, because the gain in the reward can also come if you really increase your KI point. So it becomes important to show that we are not losing too much in terms of KI divergence or making the model. It is so the gain is essentially coming from the better estimation of the Q function. And then we repeated this over 6 different evaluations and able to consistently reproduce the same results. And because reward might also be like over claiming, in the sense that because we did the reward and then we're evaluating on the same objective, so it becomes important to also do GPT-4 based evaluation in terms of win rate. And here also our proposed approach is able to perform consistently better as compared to state-of-the-art approaches. And then we also tested, as we are saying, if the reward models are very, very different, how the proposed approach performs. So we stayed within limit. So if they're very different, even the existing approach, if they are similar, the existing approaches are able to cope up and perform equivalently better. But if the difference becomes large, because there's no correction term in any of the existing state of the art, so their performance becomes very bad. But the proposed algorithm is able to still maintain the performance. And this is just one cherry-picked example, because we have shown the statistical results. So this example is just to show that, okay, we are not just doing any kind of reward hacking. It is indeed reproducing a meaningful response for a given problem. So in conclusion, we propose a novel decoding strategy, and we did theoretical analysis and also provided empirical results. So this, as a future direction, this idea would really help to develop personalized product recommendations with LLM, because we can just take the one LLM, and depending upon, we can even reward at the customer level, and we can generate recommendations or text for each of the user. Think of it like I think having a short review of the movie, right, written for you, and that could be like different, like depending on your personality. For a given movie, the description could be different for you, so that you ended up watching it, right? So rather than having a same description, and we can do that with this. And then inference time alignment can really help reduce behaviors without changing the parameters, and we believe it would have huge applications. Thank you so much.
So for the last point about personalized alignment, how much data would you need to collect from you for preferences?
Yeah, so if we want to train a reward model from scratch, then we really need a lot of samples. But we can do fine tuning on reward models also. So we can collect small responses, and then whatever the reward model we have, we can fine tune it, and that can happen with very less number of samples. Or interestingly, depending upon the personality or some text description what user wants, we can even just do prompt tuning of an LLM to behave as the human wants. So there are papers. So I don't know if there's a correct answer to this question now, because even with one prompt, we can even change the LLM to behave the way we want, and that can act as a reward model for us.
Yes, so one of the things that you're trying to do is fine tune on tokens is that you don't have to retrain the whole model. But here it seemed like you had to use a pre-tuned model.
Yes.
So doesn't that kind of defeat what you're trying to avoid
Yeah,
having
so
to do?
that's a good point. So the thing is, we don't want to fine tune a model, but there are already fine tuned model available. So we are not doing that. So we did not train them. So if they are already available and the energy and money has gone in to train them and they are fully available, why not use them and then stick to SFT? That was the argument. So we are not doing that fine tuning. It is already done, but we are correcting it for the target. So it performs better. Yeah, if there is no fine tuned model available, of course, we should not do. Yes. Yeah. Any other question? Yes.
So to do this whole thing, what do you exactly need to do in terms of like knowledge trading and so on? So is there gonna be like an additional kind of, so you have the baseline and then you have the original state, the SFT, and then you will have kind of a third thing that handles all the probability ratios. What is exactly that thing?
So the easy thing is, think of it like I have the base model, and let's just say it gives me the logics of top 5 tokens. It is going to generate. There are 5 tokens with the corresponding logics, right? And then what we do is we estimate this TQ star separately. And the TQ star will also give me the corresponding values of these tokens. And then I check. If they are in line with each other, of course I can pick. And that can give me how should I select my tokens. That's what is happening. So it will give me for all those tokens what this value function is telling me. And then I will pick the tokens from there. That's what. So the moment we know TQ star, then
It's like just a simple.
yes. So on a very basic level, simple level, it is just changing how I'm going to pick out of this top.
That's it. Thank you.
Maybe I missed this because it's early. So it's really nice that you don't have to do any retraining, but do you know roughly how much you're losing by not retraining?
Theoretically, we don't lose anything because theoretically it says that okay, we can really do it. But of course, if because there is an inherent assumption here, the baseline model needs to be good enough. It's not like I can have a uniform policy and then fine tune it with this. So the inherent assumption is base model cannot be very bad from the target. There was in the suboptimality gap, there was a term which was the difference between rho star and rho SFT. And that I can't control. That depends on how good my SFT was. If that was already very big, no matter what I do, my optimality gap is going to be very big. So there's an inherent assumption saying that that is small. If that is not small, this will not work.
Is it like completely obvious that this is an RL problem as opposed to like a supervised non-IID problem?
Maybe
Do you really need the machine learning machinery of RL here?
I think so, but I might be wrong. So I don't want to strongly comment. There might be that this is the formulation, the way I looked at it, and then people have formulated, and I find it exciting. But yeah, there might be other ways to do it. If there are, yes, I think this is a very exciting and new area. Like it's called inference time alignment. So model remains the fixed. Whatever we want to do at the inference time, and we can result in ended up generating a better response. Really nice.
Other questions?
So since everything is being done at the decoding step, are you still limited in your possible choices by the baseline model?
Yes.
Which is like narrowing the probability.
Yes. So as Mark mentioned, if my baseline model is very bad, then I think we can't do, because at least even in experiments, we just do it for top K tokens. We are not taking the full vocabulary. If those top K tokens does not capture the meaningful tokens, then no matter how good selections I do, it is going to generate garbage. So I think it really depends on it. That is why I think these ideas came now. Otherwise, means it would be really like you start from any exploratory policy and just for the token you can do that. And I think, yeah. Thank you so much, everyone. I hope it was useful.